Okay, awesome. Hi, everyone. I'm really excited to kickstart the salt marsh restoration session. And so for my talk today, I'm going to be discussing how humans have historically altered salt marsh hydrology. So thinking about water movement and distribution throughout marshes and how that is affecting our current day needs for marsh restoration. And then I'm going to give a very broad overview of a couple different marsh restoration tools, which will then be detailed in greater detail later on in the session. So as a refresher, salt marshes are these critical habitats located at the interface between the land and the sea. And this makes them very vulnerable to human activities, climate change, and sea level rise. But it also makes them very valuable habitats. They provide a number of different ecosystem services, serving as habitats and nursery grounds for a variety of different organisms, retaining and recycling nutrients, primarily nitrogen, storing large amounts of carbon, and buffering storms to protect coastlines. Hydrology drives the provisioning of a lot of those ecosystem services. So again, thinking about the movement of the water, the distribution of the water within these systems. And this hydrology in marshes is primarily dictated by tidal regime, but can also be influenced by precipitation and groundwater inputs. And so I like these two pictures because it shows you just how dynamic the hydrology in marshes can be. On the left, you have a neap tide, so a very, very low tide. And you can see that majority of the marsh ecosystem is very dry. The vegetation is not inundated. The sediments are maybe exposed to oxygen. And then about 6 hours later, during high tide, the marsh can become extremely flooded, the plant's inundated, and oxygen availability goes down. So the hydrology in marshes is very dynamic, and it's also we're seeing it changing quite a bit with sea level rise, as well as lasting agricultural activity. So perhaps a less known fact is that every salt marsh used to be a farm. And I'm going to stop for a minute and introduce the SMART teams, which they are a team of researchers and practitioners who have formed together to help us understand and really study these legacy agricultural features that are impacting marshes. And this group also provides some training for practitioners to understand how to identify these features. And then they also help provide restoration design oversight and advice. And so there's evidence that farming in marshes dates back to about the 1630s. And it was believed that salt marshes were crucial for the economy of many coastal towns. And so this is a nice depiction of how we envision some of the ways that farmers used the marsh. You can see them digging peat to build embankments, that's in the center of the screen, over a water control structure called a trunk in the middle. And so farmers learned how to manipulate and manage the hydrology to increase yield for their different farming practices. One of those farming practices was to cultivate hay. So farmers would mow and cultivate the salt marsh grasses, place them on staddles here, like pictured here, to dry. Once that hay was dry, they would then use it to feed livestock or insulate houses. And I don't know if anyone has ever seen this, but we see a lot of remnant staddles, especially in marshes on the North Shore today. So as farmers began to use the marsh, they began to really understand how to manipulate the hydrology to best increase their crop yields. And so one of the ways they did this was by digging ditches. These ditches, the purpose was to drain the marsh and help dry the sediments and dry the grasses faster. So these ditches, though, are not to be confused with mosquito ditches, which is probably the more dominant type of ditch we all see out in marshes today. Mosquito ditches were dug as part of a public works initiative in around the 1930s. The goal of these ditches was to drain the standing water and reduce mosquito breeding habitat. Currently today, many of these ditches none of them are being managed anymore, and so a lot of them are becoming clogged, which is contributing to some of the hydrology issues that we're seeing in the marshes. Back to farming, another way that farmers altered the hydrology to farm was by building embankments. And so you can see here a picture of an embankment, the little sediment mound. So farmers would excavate peat from what we call borrow ditches on either side of the embankment. And the goal of the embankments was to create an area that didn't allow water in. So that would dry the sediment and allow farmers to plant crops. And they would often create these kind of terraced systems, you can see, where the soils would go get more fresh as you moved more upland and they could plant their more valuable crops. And so these are probably some of the more predominant visual features that we see from the agricultural practices. And here's another example of an embankment, a little bit less pronounced, where you have the higher, drier grasses in the center of the photo, and then on either side you have lower elevation saturated soils. And so what's happening now with embankments is while they were really good at keeping the water off the marsh for farming, now with sea level rise, water is topping those embankments and getting trapped in the center. And when the water gets trapped, it drowns the vegetation, which causes the roots disappear, so then you're losing that root structure that holds the peat together. So we're seeing a lot of subsidence and elevation loss due to these embankments. And here's just one more visual of just how much activity the farmers had in the marsh. And most of these pictures are from the North Shore, but you can see there's a lot of legacy remnant features that are still being found today. And so if you've noticed, I've been calling this mismanagement because we're now starting to understand that this history of hydrologic mismanagement is now leading to the creation of megapools. We're seeing a very quick emergence of these interior areas of shallow standing water more closely, not on the marsh edge, but actually more towards the upland. And so what's causing that is ditches being clogged, as I mentioned, impoundments trapping water. This is another mechanism of that pool formation. So in blue, you have the gridded ditch system. And so what's happening is that those ditches lower the water table, which is causing the sediments to be exposed to oxygen. So that peat gets oxidized and then it subsides, resulting in elevation loss. So with that low elevation, that's further trapping water, killing vegetation, and creating this kind of positive feedback loop where we're continuing to lose marsh habitat. If you're wondering kind of how ubiquitous these activities are, about 90% of marshes from Virginia to Maine have been ditched. This was a study put out in 2025 where they mapped 14,000 kilometers of ditches from Virginia to Maine using aerial imagery. And so I put this picture here because this is the Burnsville Great Marsh right here in our backyard, and you can see it is a very, very heavily ditched marsh. This is what that marsh looks like without the mapping lines. So very visible with the naked eye, very visible when you're out there on the ground. And so you can imagine that all of these ditches are having an impact on marsh hydrology and increasing our need for restoring them. So loss of the vegetation, loss of the peat, expansion of these megapools are all significant drivers of marsh loss. And so if we're losing this really valuable habitat, we're going to be losing all of these ecosystem services that the marshes provide and that we've all come to rely on. So we have now begun to understand the need for hydrologic restoration. By draining some of those megapools and creating conditions suitable for vegetation, we can help the marsh increase its elevation capital and allow that vegetation to reestablish and regain habitat and provide those ecosystem services. So I'll introduce you to the restoration trio. Again, this comes from the SMART teams, and it's a trio of restoration techniques that are usually used in combination with one another. They're nature-based, they're very low-cost, low-tech, very minimally invasive, which makes them really important tools that we can use to restore hydrology if you can get through the permitting of them. So I'll walk through each of them, first starting with drainage features, more commonly referred to as runnels. These are shallow, narrow channels that are dug into the marsh surface to help drain standing water from the megapools and allow that vegetation to recolonize. So the runnels connected to a pool or an area of standing water to a drainage ditch, and it helps drain the water. Here's an example of a runnel that we installed at Webner. So you can see what the pool looked like before the runnel was installed, and then just 2 years later, you can see just how extensive the drainage has been. Moving on to ditch remediation. This is the process of essentially helping a marsh self-heal, a ditch self-heal, and this is done by mowing grasses and braiding them together and staking them down into the ditch. And the idea here is that that extra added vegetation will help trap sediments and build that peat elevation to help the marsh kind of close and raise the water table. So you can see here, this is an example from a project on the North Shore. In just 3 years, that ditch remediation has extensively helped that vegetation recover. And on the right is what it would look like, that's an untreated ditch. And lastly, microtopography islands involve the placement of small amounts of peat onto the marsh surface. And this is not to be confused with thin layer sediment placement. This uses the peat that's been excavated from runnel digging to make very small, little, like about a foot by a foot islands on the marsh surface. And the idea here is to help create higher elevation habitat for salt marsh sparrow nesting, because they like to nest in the higher marsh. And so it's a way to kind of repurpose some of that peat that we're digging from the runnels. So all three of these different techniques have slightly different approaches to restoration, but when used in combination with one another, can really help comprehensively restore hydrology. We're going to hear from Sarah Grady next on how to, she'll dig into a little bit deeper on how to plan these comprehensive projects. But what I will say is that it's important to understand the anthropogenic activity in your marsh. Understand those legacy agricultural features and address those first. Remove anything that's maybe restricting the tides, tidal restrictions, so culverts, dams, mosquito ditches that are clogged. And then ultimately, these marshes need to recover their elevation. And this can be kickstarted by vegetation recovery, but it can also be aided by thin layer sediment placement. For those unfamiliar, thin layer sediment placement is just as it sounds. You can see in the top right, you have a very healthy marsh. Top left, top right, as the sea levels rise, plants are becoming too inundated and drowning. Bottom right, if you place a thin layer of sediment onto the marsh surface, it helps increase the elevation capital, allowing plants to recolonize and keep pace with sea level rise. Here's another example from Webner, a pilot project done where you can see all the way on the left before the sediment placement, there's extensive ponding of water and vegetation death. And then in about 2 years, that sediment placement was very successful in encouraging the salt marsh vegetation to recolonize. And lastly, I'm going to end with salt marsh migration, because I think often this is thought of as a more passive approach to restoration, something that salt marshes will just do on their own. And there are ways that we can incorporate marsh migration into restoration design and practice. So thinking about the different migration corridors, forests, Phragmites stands, and agriculture. And then how we can facilitate marsh migration is by modifying behaviors such as stopping mowing to allow the grasses to recolonize and grow wildly on their own. We can protect low-lying roads, limiting development close to marsh in low-lying areas. Removing Phragmites, so you're eliminating that competition with the marsh grasses, and then also removing legacy agricultural features. So I'll just end there by saying we now have a really solid understanding of how these legacy agricultural features are impacting marsh hydrology. And by incorporating that knowledge into your restoration projects, we can create very efficient and effective restoration projects that'll help build resiliency for these marshes to adapt to future climate change.